In this section of the digital module, I'll demonstrate the use of analog modelling through a case study based on the conduit dynamics of Strombolian activity. I use this example particularly to explore how scaling considerations underpin the experiment design. And I've chosen this case study because it covers many of the standard aspects of scaling, but it also required some more detailed considerations. My name is Mike James and I'm a volcanologist in the Lancaster Environment Centre at Lancaster University in the UK. Much of the work that I've carried out in this area was done in close collaboration with my co-author Steve Lane, who's also a volcanologist at Lancaster. The module is aimed at postgraduate level students who have some experience in analog modelling approaches, or alternatively you may have gone through the first section of this digital module, which introduces some of the underlying concepts of analog modelling. So if you complete this section of the module, you should be able to use a case study of Strombolian activity to explain the advantages of using an analog modelling approach to explore volcanic processes. You should be able to describe how the concepts of similarity and how scaling arguments are used to design suitable laboratory models. Finally, you should be able to use a scaling-based approach to explore how more complex dynamics can be represented within laboratory models. In this case, these complexities are due to the rapid gas expansion that is driven by pressure changes. In magmatic conduits, these sorts of dynamics are very important in the near surface, so they're key for interpreting our observations of Strombolian or similar types of volcanic activity. So, firstly, I'll consider the underlying aims and the questions that we might tackle through using an analog modelling approach. I'll then introduce the laboratory apparatus and consider the scaling that is required. So this scaling includes the steady dynamics, by which I mean the fluid motions that don't evolve much over time. This can be carried out using conventional and well-established scaling approaches, which enable us to determine the overall similarity between the laboratory model and the volcanic system. In particular, we'll consider the relevance of matching fluid dynamic regimes rather than trying to precisely replicate particular values of the dimensionless numbers that are used in scaling. Finally, we'll consider the additional challenges that are driven by pressure changes, which are not considered within the conventional dimensionless analysis. In the volcanic system, these pressure changes result in substantial near-surface gas expansion. The rapidly changing dynamics involved underpin the activity that we observe at the surface. Thus, we would want to replicate these in our model because we're trying to represent the important near-surface processes. So, to provide context and rationale for these experiments, what are the underlying questions that they might be used to address? Fundamentally, we want to try and quantify the hazards posed by volcanic activity. Basaltic systems, this often involves trying to quantify the degassing rate, which can give insight into the rate of magma generation and magma circulation within the system. Strombolian eruptions are often relatively approachable and spectacular, so sites can become established tourist destinations. These then require careful monitoring in order to maintain safe access. So another key aim is to be able to identify potential changes in otherwise routine volcanic behaviour, changes that may precede sudden increases in hazard. To meet these aims, we need to develop a better understanding of the conduit dynamics. In particular, how does magma degas and how does the gas then drive eruptions? Understanding how these processes work is the first step, with the next step being to interpret field measurements and monitoring data such as seismics and infrasonics in terms of these physical source processes. These interpretations can then be used to inform hazard management. So these aims can be tackled using a number of different approaches, probably most obviously by field measurement. Many active volcanic systems have continuous geophysical monitoring that gives us strong statistics on eruptive activity. So, for example, on event magnitudes, event durations, and repose intervals. As I mentioned on the previous slide, we can also interpret geophysical signals in terms of subsurface processes, such as the magma fluid dynamics. However, because we can't directly observe magma motions at depth within the conduit, these interpretations usually have substantial uncertainty. So measurements can be augmented by using numerical models, such as through computational fluid dynamics. These models enable us to simulate subsurface processes and their measurable surface effects, from which we can then enhance links to geophysical data. However, large computational models can be slow and therefore expensive in time to run. Also, despite their flexibility, models are still limited by our knowledge and understanding of the appropriate assumptions and parameter values, so model results should always be independently verified. For directly observing processes, we can use analog models in the laboratory. Analog models allow us to measure signals that we can compare with geophysical monitoring data from volcanoes. However, to ensure that the models are giving useful insight into volcanic processes, they must be designed so that they are scaled to give similarity with the volcanic system of interest. So, if we're trying to get a better understanding of the near-surface dynamics of Strombolian activity, let's consider what aspects of the volcanic system might be relevant. To help define some suitable parameter value ranges, we can use Stromboli as a broadly representative type example. If you recall the terminology that we considered in the first digital module, we'll therefore use Stromboli to represent the volcanic prototype that we'll be trying to model. The part of the system that we're interested in is the near-surface portion of the conduit, so we can consider a relevant length scale to be of order 100 meters, with a conduit width somewhere between 1 and 10 meters. The conduit is unlikely to have a completely straightforward geometry, and particularly with increasing depth, probably have some sort of irregular crack type shape. In the conduit, the magma is likely to have a viscosity of somewhere between 100 to 10,000 Pascal seconds and a density of about 2,500 kilograms per cubic meter. So I've called this viscosity, which might be implying magma with a Newtonian rheology. But in reality, it's likely to be much more complex, particularly as crystallization becomes important near the surface. As we're considering gas separation from the magmatic fluid, we can also say that the gas is dominantly water and carbon dioxide, and the surface tension of the magma is of order half a Newton per meter. To represent this prototype in the laboratory, we want to consider a canonical approach that designs out the complexity of the volcanic system so that we can focus on exploring the first order process. The apparatus also needs to be practical and safe to use. So we might try and represent the conduit using a vertical tube with a length of around a meter and a width of a few centimeters or so. This gives us geometric similarity with the prototype conduit with a length scale factor of approximately 100th, but with the full recognition that this is a simplification of the real system. With these dimensions, we can easily represent the conduit using a glass tube, which is practical in a laboratory and allows direct observations of the flow. Clearly, this approach doesn't capture the geometric complexities that we know will exist in the field, but it gives us an ability to observe the first order flow processes within the practical confines of a laboratory. For a liquid to represent the magma, we can consider using water, or if we want to increase the viscosity, we can use some sort of sugar solution. These give us a range of safe and convenient Newtonian liquids that could cover a 5-order magnitude range in viscosity, and they'll generally have a density close to that of water. Again, this doesn't represent the complexities of the volcanic system, such as variable non-Newtonian rheology. However, it should enable us to explore the first order processes associated with gas separation in large bubbles. Finally, to keep things straightforward, we can just use air as our gas. This means that we can run the experiment at room temperature, and we don't need a gas cylinder supply. So you can see that the model materials are very different from those in the prototype, and their parameter values may differ by many orders of magnitude. I've already mentioned geometric similarity of the apparatus to the prototype, but we now also need to consider kinematic and dynamic similarity. However, before we go into detail on these, it's useful to first consider similarity at a phenomenological level too. This is a key initial check to make sure that we are representing an appropriate style of process. Now, we know from many engineering studies that gas can separate from liquids in a wide variety of different ways. For example, at very slow gas flow rates, small gas bubbles can ascend individually through a liquid column. We'd call this a bubbly flow regime. At very high gas flow rates, they can produce a central region of a gas jet which is surrounded by liquid. This is called annular flow. So these different styles are representing different regimes of behavior, or different two-phase flow regimes. So before considering kinematics or dynamics in any detail, we first want to make sure that our experiment will operate in the appropriate flow regime. So what flow regime do we believe is relevant for Strombolian eruptions? From field observations, we can suggest a generalized description of Strombolian activity as a relatively short and gas-rich eruption, maybe tens of seconds in duration, which ejects clots of liquid magma up to a few hundred meters or so above the surface. So individual eruptions are typically separated by longer repose intervals of order minutes or more. So we can start with a hypothesis that Strombolian activity represents the surface expression of slug flow in the conduit. The slug flow is a flow regime in which large gas bubbles, which are much longer than they are wide, ascend within a liquid-filled tube. Each Strombolian eruption is then interpreted to be the arrival of one large gas-filled bubble or slug at the surface of the magma column. In the laboratory, we can generate gas slugs within liquid-filled tubes as pictured here. The outside of the glass tube is shown by the parallel lines, and the bubble or the gas slug is here. Note that it is almost the same width of the glass tube. However, in order to travel upward, the gas slug must be surrounded by a falling film of liquid, which is travelling downward. Now we consider what factors control the ascent of the gas slug. It's likely that liquid viscosity will be an important variable because it seems sensible to assume that the liquid viscosity will influence the characteristics of the falling film. Liquid density is also likely to be important too. And actually it's the slug buoyancy that will be the key thing here. The slug buoyancy will be due to the contrast between the liquid density and the density of the gas in the slug. But if we assume that the gas has negligible density compared to the liquid, we can just simplify this to only consider the liquid density. We have an interface between the gas and the liquid, so the interfacial or surface tension is also likely to be a relevant variable. Finally, if we're thinking about the ascent velocity of the gas slug, then gravity is responsible for the buoyancy force. We might also anticipate that the tube diameter will be important. If we consider the parameter values for a natural prototype of Stromboli, then we can quantify dimensionless numbers for assessing the dynamic similarity of our model. If this is a completely novel or a new system, then we may need to derive some new dimensionless numbers, which could be done by using Buckingham pi theory. However, for most volcanological applications, relevant dimensionless numbers are already available, so I'm not going to go into any new derivations. For slug flow, the key dimensionless numbers have been well established within the engineering community, and we can draw directly on this to help us design for an appropriate dynamic similarity in our model. There are three key dimensionless numbers that help describe force balances in slug flow: the Froude number, the Ertwurst number, and the Morton number. Each characterize a ratio of different types of forces. So, for example, the Froude number describes the ratio of inertial to gravitational forces. In this equation, capital U is the characteristic velocity for which we would use the slug ascent velocity. G is gravitational acceleration, and D is a relevant length scale, which would be the tube diameter. So in flow regimes with a high Froude number, slug velocities are high, and so inertial forces are also high. For Ertwärts numbers, for very small Ertwärts numbers, buoyancy forces are much smaller than interfacial tension forces, which are given here by sigma. In some cases, this can mean that there is no fluid flow at all. Finally, the Morton number represents the ratio of viscous to interfacial tension forces. In this equation, mu is the liquid viscosity and rho is the liquid density. During slug flow, these force ratios affect the slug ascent velocity and also the slug shape. So, for example, the effect of different Ertwärts and Morton numbers on slug shape is illustrated here. Going from the left to the right of the three uppermost columns increases the Morton number from 10 to the power of minus 12 to 10. This represents an increasing importance of the viscous forces in the system over the interfacial tension forces. Within each of these Morton number sets, there are three examples for different Ertwärts numbers. On the leftmost side, going from left to right increases the roundness of the slug with decreasing Ertwärts numbers from 100 to 1. Slug shape is being increasingly influenced here by the interfacial tension forces with respect to the buoyancy forces. So, dimensionless numbers can give us insight into slug morphology in magmatic systems because within the laboratory we can observe the slug shapes easily and we can calculate the relevant dimensionless numbers to relate them to the volcanic system. However, slug ascent velocity is probably a much more important variable to consider when we're thinking about Strombolian activity. Slug ascent velocities have been extensively studied within the engineering community, and this has resulted in velocity being mapped against Morton and Ertwärts numbers. This is a rather complicated diagram but shows that mapping, and it also extends it to volcanologically relevant parameter values. On the vertical axis, we have the Froude number, which represents a dimensionless velocity. This has been plotted against the Ertwärts number for different curves of Morton number. So each curve shows a dimensionless velocity expected for gas slugs of a particular Morton number over a range of Ertwärts numbers. At the top of the graph, you'll see that all the curves tend to a dimensionless velocity of 0.345. This represents the fastest dimensionless velocity that slugs will ascend through a static liquid column in a circular cross-section vertical tube. At this point, the Froude number is large. It's as large as it can be within the system, and the slug ascent velocity is controlled by the liquid inertia. We call this the inertial regime. In the bottom left of the plot, we have very small Froude numbers and very small Ertwärts numbers as well in the viscous regime. Here the liquid viscosity is sufficiently high that it effectively controls the ascent rate of the gas slugs. So in between these two regimes, we have a transitional area where both viscosity and inertia play important roles. On the right-hand side of the diagram, the grey shaded area represents where gas slugs in basaltic magma would be expected to plot. This region covers systems in which inertia can effectively control ascent velocity, or viscosity can have an important effect. If we put in our approximate numbers for Stromboli, then we end up with a point somewhere like this in blue. This falls away from the inertial regime, so there is some viscous influence on slug velocity, but we have high Morton and Ertwärts numbers, so interfacial forces don't play an important role. So now let's return to our natural prototype of Stromboli and the parameters that broadly characterize its near-surface magmatic system. To represent this type of system in a laboratory scale analogue, we can use a smaller and simplified setup to explore some of the first order effects. With the physical dimensions of the equipment defined, to match the appropriate ranges of dimensionless numbers, we can use a liquid with a viscosity of something between that of water and about 30 Pascal seconds. For simplicity, we can also use air as the gas phase. So these numbers should provide an analog model that is well scaled and under effectively steady state conditions, slugs ascending at near constant velocities. But one thing we haven't considered in this is any variation that might occur due to the near surface changes in pressure. As a slug rises in a volcanic conduit, the pressure that it experiences will change from something close to magma static pressure at depth, decreasing to something like atmospheric pressure once it has reached the surface. So, considering this static pressure change for Stromboli, over the length scale of approximately 100 meters, we can compare the pressure at the depth of 100 meters in the magma column to the pressure at the surface. At the surface, we have atmospheric pressure at approximately 100 kilopascals. Within the conduit, for a magma density of 2,500 kilograms per cubic meter, we have a pressure gradient of 25 kilopascals per meter. So this means that the pressure at scale depth is approximately 2.6 megapascals, or 2,600 kilopascals. As the slug rises to the surface, it will decrease pressure, decompressing from this pressure to atmospheric pressure as it ascends over approximately that 100 meters. If we consider this change in the static pressure alone, then we would expect the gas bubble to expand by approximately 26 times, or 2,600%. You can see why we might expect a violent burst at the surface. Now, let's carry out the same estimation for the laboratory, where we have a length scale of 1 meter, a liquid density of approximately half that of magma, and a surface pressure of the same 100 kilopascals, or atmospheric pressure. So we have a slightly smaller pressure gradient, but critically here, we have a much smaller length scale. So the pressure at the scale depth of 1 meter is only slightly greater than that of atmospheric pressure. Consequently, as the gas ascends over that meter, we would expect only very limited expansion. Thus, there's clearly a scaling issue here. There are 2 orders of magnitude difference in what we would expect in terms of gas expansion over the model and the prototype length scales. So you might think of this as giving some sort of kinematic scaling issue. The relative change in slug length in the prototype is not well represented within the model. We can consider the implications of this by thinking more about what happens as a gas slug expands rapidly as it ascends towards the surface. As the slug ascends, it will be exposed to a minimum pressure that's given by the static pressure in the magma directly above the slug nose. During ascent, the liquid column above it becomes shorter, reducing this static pressure and allowing the slug to lengthen. However, as the slug becomes longer, more liquid becomes contained within the falling film surrounding it, further reducing the head of liquid above the slug and thus further reducing the static pressure, promoting more gas expansion. So this is potentially a runaway process, with the expanding gas continuing to expand because, as it expands, further decreases the pressure from the head of liquid above it. So in the near surface, we can think of this as a runaway process that culminates in slug burst. Essentially, large slugs in the near surface can be considered unstable if only static pressure is considered. There's not enough liquid above them for pressure to be controlled purely by the static pressure alone. So this means that the gas expansion must be sufficiently rapid so that the dynamics associated with it are important. To expand, a slug needs to move liquid out of the way. When expansion is rapid, The inertia of this liquid hinders that expansion, leading to a dynamically generated overpressure within the slug. So in Strombolian eruptions, it's this gas overpressure that causes the magma clots to be ejected into the atmosphere when the slug bursts at the surface. So at depth, as a slug is ascending, it's only expanding relatively slowly, and it can be considered as stable, even if we consider only static pressure conditions. But at some point, it may reach a critical threshold depth, where its rate of expansion means that the evolving dynamics have an important effect on the slug length and pressure. So what influences this critical threshold depth? One clear factor is how much liquid is being drawn into the falling liquid film. A thicker film will effectively reduce the depth of liquid above the slug more quickly, so might be expected to lead to deeper critical threshold depths. We can non-dimensionalize this by considering the cross-sectional area of the falling liquid film with respect to the cross-sectional area of the gas slug itself. We can represent this simply by A prime, which is the fraction of the tube cross-sectional area that is occupied by the falling film. We can then draw on extensive engineering studies to characterize A prime across a wide range of fluids based on a non-dimensional inverse viscosity. Thus, we can estimate A prime from key parameters such as gravity, liquid density and viscosity, and tube diameter. So using parameter values appropriate to Stromboli gives an inverse viscosity of about 40 and A prime of about a half. So approximately half of the conduit cross-sectional area is expected to be filled with a falling liquid film. In the laboratory, for a water sugar solution with a viscosity of a Pascal second, we can see that the calculated inverse viscosity and the A prime values are relatively similar to those of the prototype. This actually shouldn't be a surprise, given that our system should be generally well scaled for viscosity through the other dimensionless numbers that we've covered earlier. Now we have the A prime values, we can use them to consider a metric for slug stability, gamma, which is also a dimensionless number. So gamma is a slug stability index. I'm not going to go and derive it here, as this is beyond the scope of this module, but if you are interested in its origins, then you can refer to the papers cited here. Gamma incorporates the terms that we've seen previously are likely to be important: surface or ambient pressure, the anticipated slug length at ambient pressure, and liquid density. Now for gamma values of less than 1, a gas slug can theoretically rise to the liquid surface at near static pressure. This means that any dynamic overpressure within the slug is relatively small, and we'd expect a relatively low energy slug burst at the surface. Looking at the equation for gamma, this situation would occur for high ambient pressures, very small slugs, low density fluids, and for slugs surrounded by thin falling films. Experimental data and modelling results show that when gamma exceeds approximately 2, we can start to see increasingly important dynamic overpressure being developed within the gas slug. This can be for increasingly long slugs, increasingly thick falling films, which would result from more viscous magma, or for reduced ambient pressures. So one thing to note here is to calculate gamma for our prototype system at Stromboli, we can estimate A prime. We know that the atmospheric pressure, and we know G, and we can measure the magma density, but we would have to estimate the expected slug length at atmospheric pressure, i.e. we'd need to estimate the mass of gas in the slug. So let's look at gamma for the two systems, prototype and the model. First of all, Stromboli. Because we observe energetic gas bursts in the field, we can see and infer that gamma exceeds 2. So from the equation for gamma, we can then estimate that the expected length of a slug at atmospheric pressure is likely to exceed 10 meters. In the laboratory, we can easily measure the volume of gas injected for the slug, so we can calculate the expected slug length at ambient pressure, which might be of order 10 centimeters. We can then calculate gamma, which turns out to be less than 1. So the analog and the prototype are in different regimes here. At Stromboli, field observation shows we expect dynamically driven overpressure to be important, but in the lab, gamma indicates that experiments would not be generating any significant dynamically driven overpressure. So in the lab, A prime, and rho, the fluid density, would actually be difficult to substantially change due to the other requirements for the liquid. However, another way forward would be to change the surface pressure at the top of the liquid column. So for example, if we decrease the surface pressure to somewhere between 100 and 1000 pascals, this would give a gamma range up to about 4, and therefore will enable us to explore the unstable slug regime that is associated with energetic bubble bursts. Gamma can also be increased further by using larger gas masses, i.e. by increasing La. Thus, carrying out experiments with a reduced surface pressure would enable us to scale for the kinematics and the dynamics associated with pressure changes during the slug ascent. However, there's one important implication of this. If we use water as our liquid, the low surface pressure would result in substantial vapour entering as a gas phase into the gas slug. So ascending gas slugs would then grow not only by decompression, but also by the host liquid transforming into gas. Thus, the mass of gas within a slug wouldn't be constant during ascent. This would really complicate the evaluation of any results. So to facilitate using a low atmospheric pressure, we also need to use liquid with a vapor pressure of less than about 10 pascal seconds at laboratory temperatures. So we can meet this scaling requirement by using an organic oil as our liquid. It's the sort of oil that's typically used in rotary vacuum pumps. These oils have a slightly lower density than water and a greater viscosity. They're also much more costly. Now we can accommodate these factors by using a slightly smaller tube than we might do with a water-based system. So, summarising the system's materials, geometry and conditions, we can consider using an oil with a slightly lower density and higher viscosity than water in a tube of a few centimetres in diameter. The surface pressure can be reduced to approximately 300 pascals, and we can explore slug lengths of around 50 to 500 millimeters, which represent lengths of roughly twice to 20 times the tube diameter. We can consider this system to be kinematically and dynamically scaled, including the rapid changes due to near-surface gas expansion. Reflecting back on the real complexity of Stromboli, remember that we're not attempting to reproduce a fluid density and rheology that change with depth, or the fact that the conduit is highly unlikely to be a constant diameter vertical tube. In the laboratory, we've designed out this complexity in order to try and isolate the first order process and explore the underlying process controls. We recognize the complexity of the real system, but we are deliberately neglecting these higher order details in order to focus on the main underlying process. So using these types of scaled experiments, we've been able to get a better insight into the relationships between measurable geophysical signals at volcanoes, such as infrasonics, and parameters such as erupted gas mass. The laboratory measurements have provided the insight to guide theoretical modelling that links slug burst overpressure with gas mass. These models then enable predictions, which has been shown to be consistent with field measurements from events ranging from gentle puffing type degassing activity to much larger explosions at Stromboli. The work carried out by Del Bello et al. Also showed that burst overpressure can be even greater if magma is able to overflow from the top of the conduit during slug ascent. You can understand this because any magma loss from the top of the conduit above the slug increasingly reduces the overburden pressure on the slug and hence promotes rapid gas expansion. So in summary, we can use laboratory analog models to construct simplified representations of complex processes in order to gain insight into magmatic events. By using suitable scaling, we can ensure that the model represents the key aspects of the processes of interest and does that appropriately. If the system evolves rapidly, then scaling can be challenging and may require some alternative thinking. When carrying out the scaling for dynamics, it's not normally necessary to directly match dimensionless numbers between the model and the prototype, but rather it's critical to ensure that the dimensionless numbers indicate that an appropriate regime of control is operating. For example, viscous or a mixed inertial viscous regime in our case. Finally, laboratory models are never used in isolation, so insight from them can be used to construct predictive models from the prototype, which are then validated by field data from direct observation. This work has drawn on a number of references, which I will now leave you with in these final two slides.